This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 6, Lesson 9, Combustion and Fuels. In Week 5, we burned fuel in a boiler and stopped at efficiency. Chapter 10 is where those numbers actually come from, and this lesson computes with it. We'll turn a heating value straight into combustion air using the printed one-step table. Do the same job exactly from a balanced reaction. Work percent theoretical and percent excess air. Correct a gas meter back to standard conditions, and finish on the 140 rule that decides whether flue gas condenses inside your boiler. Concept: heating value and heat of reaction. Week 5 already read the fuel table and computed boiler efficiency. Here we go with the chapter underneath it. 2 heating values, and every later number rides on which one you used. The higher, gross, or total heating value includes the latent heat of vaporization of the water the fuel's hydrogen makes. The lower, or net value, excludes it. That water leaves as vapor. Underneath both is a heat of reaction, the sum over products of the stoichiometric coefficient times the heat of formation, minus the same sum over reactants, at a standard state of 25 Celsius and 1 bar. Burning with oxygen is just that reaction with a name, heat of combustion, and its principal products are CO2 gas and liquid water. That liquid is exactly why the printed values are the higher ones. Setup: air straight from the heating value. You don't have to balance anything to get combustion air. The handbook prints a one-step approximation. Take the fuel's heating value in BTU per pound and multiply by a constant fixed by fuel class. Solid fuels use 0.00073 for pounds of air per pound of fuel. Liquid uses 0.00071, gas 0.00067. There's a parallel column of volumetric multipliers, and each row carries its own precision. 3% for solid and liquid, 5 for gas, plus named exceptions. That result is theoretical air. Real burners supply more, and the extra is measured against theoretical air, never against the air already supplied. Setup: the exact root. When the problem hands you a chemical formula instead of a heating value, balance the reaction. The handbook models air as 3.76 moles of nitrogen per mole of oxygen. So stoichiometric methane in air gives carbon dioxide, 2 waters, and 7.52 nitrogens. Excess oxygen shows up as oxygen on the right. Incomplete combustion burns some carbon to carbon monoxide instead. 2 air-fuel ratios come off that equation. The molar one, moles of air over moles of fuel, which the handbook marks with an overbar, and the mass one, mass of air over mass of fuel, which is the molar ratio times the ratio of molecular weights. Then percent theoretical air is actual over stoichiometric times 100, and percent excess air is actual minus stoichiometric over stoichiometric times 100. Solve. Coal. A bituminous coal has a higher heating value of 14,000 BTU per pound and fires with 30% excess air. It's a solid fuel. So take the solid row. 14,000 times 0.00073 gives 10.22 pounds of air per pound of fuel, theoretical. The volumetric multiplier gives 135.8 cubic feet per pound. At 30% excess, multiply by 1.3, 13.29 pounds of air per pound of fuel, or 176.5 cubic feet. That 1.3 is just the excess air definition rearranged, and it self-checks. The handbook's per fuel table lists bituminous coal at 10.3, so we're 0.8% off, well inside the 3% the table claims. Solve. Percent theoretical and percent excess air. Now the methane burner. From the balanced equation, the molar ratio is 2 plus 7.52 over 1, 9.52 moles of air per mole of fuel. Scale that by the ratio of molecular weights, and you get about 17.2 pounds of air per pound of fuel. The handbook prints 17.24 for methane, so take the printed value. Our burner is measured at 20.7. Percent theoretical air is 20.7 over 17.24 times 100, 120.1%. Percent excess air is the difference over the same denominator, 20.1%. They differ by exactly 100, and they always will. Subtract 1 inside the first fraction, and you've got the second. And notice this is week 5's excess air in different clothes. Both ratios carry the same fuel mass, so actual over stoichiometric is literally air supplied over theoretical air. One quantity, two printings. Automatic fuel burning systems. A gas meter measures volume at whatever the gas is doing inside the meter, not at standard conditions. So the input rate corrects it. Heating value times volumetric flow rate times standard temperature and meter pressure over meter temperature and standard pressure. Standard is 520 Rankine and 14.735 pSAA. The meter values are absolute. Take 5,000 cubic feet an hour of 1050 BTU gas metered at 80 degrees and 15.7 pSAA. The correction is 1.026, so 5.25 million BTU an hour is really 5.39. Altitude runs the other way. Local heat content is the heating value scaled by local barometric pressure over standard, so at 12.2 pSAA, that same gas delivers only 869 per cubic foot. The supply side gets one more lookup, the steel gas pipe capacity table, in cubic feet per hour by size and length. A worked read, an appliance drawing 120 CFH at the end of 50 feet. 3/4 inch carries only 115, so the line steps up to 1 inch, which carries 215. Watch the printed basis under the table. Half a psi or less, a pressure drop of 0.3 inches of water, and a specific gravity of 0.60. A longer run or a heavier gas takes the capacity down from there. Flue gas condensation. Burning hydrogen makes water vapor, and that vapor has a dew point. The handbook prints it per fuel: methane 139, ethane 134, propane 131, butane 129, hydrogen 162, plus a chart against the fuel's hydrogen content and its flue oxygen. Hence the rule: in a non-condensing boiler, the return hot water temperature must stay at 140 minimum to keep flue gases from condensing inside the boiler and causing damage. Notice how tight that floor is, 1 degree above methane's printed dew point. A condensing boiler inverts the rule. It's built to take cold return water on purpose, condensing that vapor to recover the latent heat that separates the higher heating value from the lower. Traps. 5. 1. Excess air divides by theoretical air. Dividing by the air supplied is the planted distractor, and it underreports every time. 2. Keep both ratios on the same basis. Methane is 9.52 on a molar basis and 17.24 on a mass basis, the same burner. Put a mass actual over a molar stoichiometric and the percentages are nonsense. The molecular weight ratio is what moves between them. 3. Only one of the two printings carries the times 100. The excess air definition returns a fraction you scale yourself. Percent excess air already includes it. Double multiply and you'll report 2000%. 4. Percent theoretical air equals percent excess air plus 100. 120% theoretical is 20% excess, never 120. 5. The one-step table is an approximation running on BTU per pound, good to 3%, 5 for gas, with printed exceptions for wet fuels, gasoline, kerosene, and lean gases. Quick recall. Higher heating value includes the product water's latent heat. Lower doesn't. The heat of reaction is products minus reactants from heats of formation at 25 Celsius and 1 bar. Theoretical air comes one step from the heating value. 3 multipliers, 1 per fuel class. Excess air is supplied minus theoretical, over theoretical. Air is 3.76 moles of nitrogen per mole of oxygen, and the air-fuel ratio comes molar with an overbar or mass without one. Percent theoretical air is actual over stoichiometric times 100. Percent excess is that minus 100. Gas input rate corrects the meter to 520 Rankine and 14.735 pSAA. And a non-condensing boiler needs return water at 140 minimum. Golden rule: air supplied over theoretical, percent theoretical air, and percent excess plus 100 are all the same number. Take whichever printing the problem hands you. Next up, Lesson 10, System Integration Review. We've taken the building apart chapter by chapter. Now we put it back together. We'll cover all air, all water, and air-water systems, what each family moves through the building, where the central components sit, and how a mixed air temperature, a changeover temperature, and a chilled beam decide which one fits a given load. Everything's at PEPrepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.